Hello everyone, welcome to the fourth lecture of week 5 of our course on AI for Earth observation. In this week, we have been discussing different techniques, problems, examples with respect to SAR image analysis using deep learning. In the first lecture, we have briefly seen several such problems. We have discussed how using SAR images can be beneficial, and subsequently in the second and the third lecture we have expanded our discussion specifically on a class of problem called object detection. Object detection, as we have seen in the third lecture, is widely adopted in several problems that use SAR image as input. In today's lecture, we will expand our discussion on deep learning in SAR image analysis, talking about classification, semantic segmentation, and several techniques that probably can be used in classification, can be used in semantic segmentation, or possibly can also be used in object detection. So with this background, let us move ahead. The first problem that we want to discuss in SAR image analysis pipeline today is about the speckle noise. This can be considered as a part of pre-processing SAR images before going ahead with subsequent deep learning pipeline. Speckle noise indeed is one of the key features which we need to keep in mind when we work with SAR images compared to optical multispectral images. Speckle noise appear as a show a grainy appearance in the SAR images. Speckle is not additive noise, rather it is multiplicative noise, and thus filtering methods are often applied before further image processing with the SAR images. We try to apply some sort of filtering methods to remove speckle noise, which we call despeckling. This could of course be based on some traditional filters. However, the focus of today's lecture, what we'll be talking about in next few minutes, is rather more on the side of can we also use deep learning or deep networks for this despeckling part as well. So before going ahead further with this discussion, one point to keep in mind is that generally we would not have a supervised data set for such despeckling talks. So we need to somehow, if we want to apply our ASVL training kind of mechanism, we need to somehow generate the data set. So to summarize, the deep learning based despeckling methods, generally synthetic data sets are used in this context, as I just mentioned, right, in the last slide, that usually we will not have a supervised kind of data set for such tasks. So we need to somehow generate synthetic data sets. Architectures for such tasks are generally similar to what we see for semantic segmentation. Rather often, what we would see is that most of the works usually use like quite shallower. I'm saying shallower, right? I'm not really saying that, okay, one layer or something like that. However, like, okay, like if you're rather, let's say, like doing a semantic segmentation on a computer vision data set, you might be using like many layers, could even go up to like, let's say, 50s or 100s, which is not most of the time not the case if we are talking about despeckling. Often it's also the case that, okay, we would do some kind of modification in the loss function to account for the specific task here. With this, let us see a few specific examples. The first example that we are looking at is called IDCNN, Image Despeckling Convolutional Neural Network. So pretty straightforward name, right? Like it's proposed in the context of despeckling. So image despeckling ID, and it's using CNN. So CNN. And this follows the same paradigm of the synthetic speckle dataset that we just discussed in the last couple of slides. That is, it constructs a synthetic speckle dataset for training. How to generate that? To generate that, it follows fundamental properties of the speckle, such as following multiplicative model with gamma distributed noise. So what we are basically saying is that we know like speckle noise follows these properties. What we can do always, think of it like we are working with a Python code. So inside the Python code, we can always, simulate these properties. So we started with X, okay, and after simulating these properties, we get, let's say, X cap, right? So X cap. Now, for despeckling purpose, your input to the model becomes X cap, and the output that you are looking for now becomes rather X. So looking at the architecture of IDCNN, this uses 8 convolutional layers that forms the noise estimation backbone. This has like layer 2 to layer 7. This uses convolutional batch normalization, ReLU, such blocks, whereas L1 and L8, they are convolutional ReLU without using the batch normalization. Additionally, it's using zero padding to preserve the spatial size. So this is a very important aspect here we have to understand. We don't really want to down sample, right? Like we want an output which is the same size as our input in this case. That's why what we're doing is that we are using padding to preserve the spatial size. Additionally, we are not using any downsampling layers. You would recall from our discussion on semantic segmentation how it works. Like in the case of the semantic segmentation, we use downsampling, means we rather later we will need also upsampling layers, right? So in this particular IDCNN, we are entirely skipping that. We are not using any downsampling layers. The final layer outputs a single channel speckle estimate, okay? And this has the same spatial size as the input itself. To talk a bit about the loss function used in the IDCNN, Euclidean loss is used to enforce pixel-level accuracy between the reconstructed image, or rather like the noise and the ground truth noise. Additionally, what we also use is in this particular work, total variation loss is also used, which is used to encourage smoothness, and basically a combination of the above two loss is used. So the first one is like, okay, like what we are doing is a regression task. So to account for that, the first loss, why are we using the second loss? Let us talk a bit about that for a while. So what is the intuition behind this total variation loss? Imagine you are walking across an image pixel by pixel. Now, if the neighboring pixels have similar values, the walk will be smooth, right? Whereas, let's say like you have neighboring pixels with dissimilar values. It can, of course, happen sometimes, but if it happens very rapidly, I mean, not rapidly, rather very frequently, that is something not expected, right? So many unnecessary jumps usually correspond to noise. So total variation, what it does is it measures the total amount of change between these neighboring pixels, and accordingly it formulates the loss. I'm not going into like the exact equations and all, but this is the intuition behind the total variation loss. Now, of course, there are also example works that have used deeper architectures. So this is one particular example. The exact reference is given in the footnote. If you're interested, you can have a look. So in this work, what they're doing is that they're using 17 layer CNN. And when we are going for, so we already said this assumption that, right, that since this is, I mean, this is a bit different task than our usual semantic segmentation, I said that, okay, like probably for this shallower architecture would be fine. Now, if you are going for deeper architecture, of course, you need to apply appropriate regularization. So one specific regularization that has been, I mean, emphasized in the paper itself. It's not that the previous example that we took, they also had actually batch normalization, but in this case, we are mentioning it with a bit more emphasis that it's used as regularization to stabilize training. Furthermore, they also use skip connections from earlier layers to the inner layers. Now, one aspect in the context of despeckling that needs to be understood is the spatial variation. Different areas, if you look at, let's say, urban area, or if you look at, let's say, like vegetation, like crop, agricultural area, all these areas may need different processing for despeckling. In fact, you may even like to leave like some areas to be unfiltered in the despeckling. So this specific property of spatial variation has also been considered by several works, including the one that has been provided in the footnote again. So yeah, I mean, if you are, let's say, designing your own despeckling framework, or like despeckling is a part of your like SAR image analysis framework, this is something to keep in mind, that depending on which particular areas that you are looking at, or let's say your targeted is a big area consisting of urban areas as well as agricultural as well as forest, you may think about like, okay, like do I provide similar kind of filtering to all the areas? The answer most of the times is no. Another interesting approach for despeckling that has also emerged is using multi-temporal SAR. Multitemporal SAR images, they provide us with multiple noisy observations of the same scene. Thus, what we can do is we can consider them as two independent realizations drawn under the same conditional distribution. And with this assumption, we can design this speckling mechanism that in a way, like you can think of like, since these are two independent realizations, this in a way is like a kind of providing pseudo supervision to each other. Let's now move beyond preprocessing. Despeckling, of course, is a very important aspect in SAR image analysis, but this is indeed still a part of preprocessing. And many of the times, of course, you'd probably just use some traditional filter instead of going for deep learning based despeckling. I have also seen like there are several works, again depending on which particular areas and all they target at. Sometimes despeckling part in the deep learning area mostly, despeckling part is even omitted and directly researchers go for architecture design, considering the downstream application itself. So, as we have already mentioned in our previous discussions, especially lecture 1 of this week, that many SAR analysis talks use optical images in one form or the other form. Now let us try to understand like how the SAR and optical images can be used together, or like how optical images can provide a kind of like pseudo supervision, or like can they like provide some kind of help in the SAR pipeline. One possibility regarding this is sensor to sensor conversion. How does this work? This is something actually we have already discussed before. So take a pause and try to think about this, like how this could be done. This has been done in the previous weeks. Okay, so this is the answer, right? Like we can use cycle GAN in this context. Cycle GAN, where we have this input A and generated A to B, which creates generated B from the input A. Another generator B to A, which creates the recovered A from the generated B, right? We accordingly, so not just two generators, we also accordingly have two discriminators. And we have talked about previously like which all loss functions and all we'll be using in this context. Now, here in this case, we can train in a way such that our input A is, let's say, SAR images, and our generated B, or A domain is SAR images, B domain is optical images. And thus, like once the training has been done, thus later, let's say we can, even if we have like optical trained model for like our downstream applications, we can first use cycle GAN and the generator A to B more specifically to convert a given SAR input to optical input, and then simply apply our optical trained model for the downstream task. This obviously, I mean, this doesn't really work that well in many applications due to the artifacts, or rather like imperfect translation from the SAR image to the optical images. So here are a couple of points probably also needs to be emphasized again. One is that why are we talking specifically about cycle GAN? Is that the only option? No, right? There could be, let's say, like peaks to peaks and other possibilities. I have a cycle GAN. This training cycle GAN, this will not need really paired SAR and optical images. this will just need, like the SAR and the optical images from the similar distribution in our more geographical terms, let's say like images, let's say taken from the similar geographic area and all. Otherwise, we'll not really need like paired images. So this is one advantage. The other point that is important to note at this point of time is also that probably standing in 2026 or so, one could also think in the terms of diffusion models. And this is something, we will be covering later in the course. Okay, so this is one option, as we said. However, another more practical possibility is knowledge distillation. Knowledge distillation is also something we have already touched to some extent in this week already. So yeah, let us go ahead. So knowledge distillation, how generally it looks like, I'm not talking in the terms of optical SAR images or anything. I'm just talking in a more general terms. What we have generally is like, let's say like a given input, a teacher network, a student network. From the teacher network, we are getting, let's say, logits. From the student network, we are getting logits. And using this, we design some kind of distillation laws. So we want that our student network, like this, is kind of like mimicking the teacher network, right? And at the same time, we are also performing classification on the student network. So with the student network, like we also want to train it for our downstream task. So it should mimic the teacher network as much as possible, but also at the same time with whatever, like often such distillation happens with limited, like when we are trying to distill the distillation stage itself. I'm not talking about the training of the teacher network, which has happened separately. The distillation itself often works under limited annotated data paradigm. So this is the knowledge distillation more generally. Now let's think about, like optical to SAR or SAR to SAR knowledge distillation. The figure that we're seeing here, this is in the context of like SAR to SAR, like two types of SAR. Let's say one is X band, one is C band, or something like that. However, of course, the same picture would be applicable if we were talking about optical to SAR as well. And this basic idea that we are looking at in this particular slide, this has already been discussed when we talked about object detection, right? Like if we have this SAR type 1, which has a frozen encoder, we get the feature vectors from this, and SAR type 2, which has a trainable encoder. From this, we are getting the feature. Now, the features from the SAR type 1 and the SAR type 2, we are trying to align their distribution. And at the same time, we are also training the SAR type Q for our particular downstream tasks. In this case was object detection. Now let us rather look at, like more in the classification context. That probably is a bit more easier to understand, right? So classification context, I also changed the input here and I'm back to the optical to SAR knowledge distillation. That's why you see now previously there were like SAR type 1, SAR type 2 in the previous slide. Right now what I have is optical image with the frozen encoder and the SAR image where we are trying to train the encoder. With the optical image, and the SAR image, we are getting the logits and we'll be having like some kind of distribution matching or distillation loss there. And at the same time with the SAR image from the logits, we are trying to perform the classification. Now, interestingly enough, this can also be actually converted to a multi-teacher knowledge distillation also. So you can always say that, okay, I just don't have one type of optical images. I have like a number of optical sensors and model for each of them, or even like optical and like another SAR sensor for which I already have the model, and another type of SAR sensor for which I'm trying to train an encoder, right? So we can also, like with some modifications, we can also design the distillation in this way that the distillation now happens between not just the like the target sensor type and just one shows rather like multiple of them. This possibility is also there. Yet another approach of combining optical and the SAR pipeline is to estimate parameters from the SAR images that are as well estimated from the optical images. So this is something, I mean, more in the direction of the self-supervised learning, and this particular strategy has been widely used in more recently, like like the foundation model era. So what I'm talking about, let us go a bit more details into this. So one example possibility is that, let's say, the normalized difference vegetation index, right? We can use, let's say, semantic segmentation architecture such as UNIT, and we can use regression specific losses. We can even use like some auxiliary input as well, like let's say elevation, but let's not think about that. Okay, that's not central to our discussion at this point of time. So at this point of time, the main point to understand is that normalized difference vegetation index, this what you do generally, you generally estimate this from multispectral images, right? From the particular NIR and all multispectral bands with a simple equation, let's say you derive the normalized difference vegetation index. But this is not a concept code to the SAR images, right? You will not generally like estimate normalized difference vegetation index from the SAR image. So now, given a SAR input, why not use a model, deep model, to predict the normalized difference vegetation index value? Okay. While learning to predict this normalized difference vegetation index value, the assumption is that the model will have to learn meaningful feature representations. So this is normalized difference vegetation index. Instead, something else also could be used there for predicting. Now, let us go ahead with discussing how to address several aspects of the SAR images. One aspect, of course, we have talked about previously, like in the beginning of today's lecture, about the speckle noise, despeckling aspect. Another interesting, so these are like what we're talking about is like the aspects which are very, important in the SAR image analysis, and either missing or not so much important when we talk about the multispectral optical images. So another important aspect is the look-in angle, which plays a very important role in the SAR image analysis. And in this context, what can be done is, like you can create some kind of angle aware classification. Let's say like we have image at a specific angle. You have an encoder, and think of like encoder followed by an identity function for now, and you get a feature map, and on the top of the feature map you have like a classifier. Let's say we are doing classification, of course it could be something else, object detection or something else as well. Yeah, I mean, but this gives us the basic idea, right, of the pipeline. Now, to work with different angles, how do you need to like alter this particular architecture? What we need to do is, now let's say we have angles, and we need to like somehow have like a feature transformation module coming after the encoder. Okay, so which in a way, like let's say the angle information, this let's say is encoded in the proper form. Okay, now this feature transformation module, this should be able to like ingest this angle encoding or angle difference encoding, and then perform some transformation on the features after the encoder, such that the feature maps now you are obtaining. Okay, so you have the features after the encoder, then the feature transformation module, which takes into account the angle difference information, okay, and transforms the features in a way that now the feature maps. Okay, this is something which has already accounted for these angle differences, and now you feed these feature maps to the classifier. This aspect will come back again when we talk about applications in one of the subsequent weeks. Let us also take another interesting use case, that is the example of the polarization, which is also very important in the case of SAR images, right? So think about like, let's say you have VV and the VH polarization, and let's say like you have this specific encoder for the VV polarization, specific encoder for the VH polarization. You take them and you feed to a decoder. Okay, the features that you have obtained from these two encoders, you concatenate or something from both of them and you feed to a decoder, and then the decoder produces output, right? Now, one important question, kind of practical scenario which may arise in such situations is that what if like during the training, let's say you collected the data set and in a way that you had this VV and VH polarization, but during inference time, let's say like when we're actually deploying your model, let's say like you have sometimes either one of these polarization, right? You don't have both polarization at the same time. You may have sometimes, but sometimes it's like one of the polarization is missing. So what could you do to account for such missing polarization during the test time? This translates to like a problem which in a more machine learning terms is like missing modality during inference. And there are several things that you can do. One possibility is that during the training time itself, you don't always feed both the polarization. Sometimes you feed one, sometimes you feed another, sometimes you feed both of them. Okay, so as if like during the training time itself, you have prepared your model to account for sometimes like missing polarization, such that during the inference time, when it gets partial information, it can still work based on the meaningful information that it has got from one of the input. Then on the top of that, several other modification is also possible. We'll not go into those details. So we'll stop here. We'll continue our discussion on SAR image analysis in the next lecture. Thank you.